which row in the table below shows the atomic structure of this ion here? So we've got a manganese 2+ ion with an atomic mass of 55. So if we look in our periodic table, we can see that manganese has got an atomic number of 25. Therefore, that means the number of protons inside our manganese has got to be 25. So we can eliminate row C and D from our table, and our answer has to be either A or B. So now let's think about our number of neutrons. So our number of neutrons we can work out from our atomic mass. So the atomic mass is the sum of the protons and neutrons within the nucleus. Therefore, to work out our number of neutrons, we have to do our atomic mass and subtract our number of protons, which we've identified as 25, therefore giving us a number of neutrons of 30 overall. And this gives us option A as our answer if we're comparing between rows A and B, and we can confirm this with our number of electrons. So our number of electrons in a neutral atom is going to be equal to the number of protons. However, we've got a 2+ charge. Therefore, the number of electrons in our ion is going to be 25, subtract 2 because we've got a 2+ charge, which gives us 23 overall. Therefore, our answer is option A. A group 2 element reacts with water to form a solution and a gas. And for this question, we need to identify which statement is correct. So let's start by writing out a general equation for the reaction of a group 2 element with water. So we're going to call our group 2 element X to show that it's a general element. And we're reacting this with water. And when we have the reaction of one of our group 2 elements with water, we're going to produce a hydroxide solution. And this will have the formula of X with 2 lots of the hydroxides. And that's because our hydroxides are a 1- charge. And because our element is from group 2, that will form a 2+ ion. Therefore, we need 2 of the hydroxides to balance out that 2+ ion. And then the gas which we're going to form is going to be hydrogen gas. So therefore, to balance this, we would need to put a big 2 in front of our water so that we have all of our elements balanced out. So let's work through these statements now and see which of these could be correct. So statement A says that the reactivity of the elements decreases down group 2. Now this statement is actually going to be incorrect, and the reason why is because as we're going down group 2, our atomic radius is going to increase, the shielding is going to increase, and therefore it's going to be easier to remove the electrons from an element as we go down that group 2. Hence they're going to be increased in reactivity. And this is despite the increasing nuclear charge. So overall, our reactivity will actually increase. Hence statement A is incorrect. Now let's have a look now at statement D. Now we can eliminate this statement because we've already written out our equation here. And the reason why this equation they've written out is incorrect is because they've got the wrong formula for their hydroxide, which in this case they've used with strontium. Because strontium is a 2+ charge, therefore the formula would need to be SrOH2. And this has affected the balancing as well. So this statement is incorrect. The reaction is not a neutralization because we haven't got an acid reacting with a base, so we don't have a proton donor and a proton acceptor. And actually this reaction is a redox reaction where we have a change in oxidation numbers for our element from group 2 and for our hydrogen there. So it's not a neutralization. Therefore our correct answer is B, and the reason why this is correct is because when we produce this hydroxide with our group 2 element, As we go down the group, as I mentioned before, the atomic radius as we go down the group is going to increase as we have increased number of electron shells. And what this means is as we go down group 2, the 2+ ion which we form is going to be less charge dense because that charge is going to be spread out over a larger volume of that ion. Hence the ionic bond within the hydroxide will be weaker, so it will be more able to donate those hydroxide ions, which will give it an increased pH overall. Therefore, our answer is option B. Chloroethene, the structure here, is prepared in the presence of a solid catalyst using this equilibrium reaction, which we can see here below. And the enthalpy change for the forward reaction here is plus 51 kilojoules per mole. And we need to identify which change will result in an increased equilibrium yield of our chloroethene. So let's go through these options and see which one will give us the increased yield for chloroethene. So because we've got an equilibrium, we can use our Le Chatelier's principle here to help us with our conditions. And Le Chatelier's principle states that when an equilibrium is subjected to change of conditions, it will shift and favour the reaction which reduces the effects of that change. So, for example, if we increase the pressure of our equilibrium system, then the equilibria will favour the reaction which reduces that pressure back down again. And for our system here, the reverse reaction will be favoured because this produces the smallest number of moles, because we produce 1 mole in the reverse reaction and the forward reaction produces 2 moles. So therefore, increasing our pressure will not increase our equilibrium yield of chloroethene. So we can eliminate option A. Now we were told that we're using a solid catalyst here, and because we've got a gaseous system, that means that this is a heterogeneous catalyst. But increasing our surface area of this catalyst will increase the rate of reaction for both the forward and the reverse steps. So overall, we will not get an increased yield of our chloroethene because although we're increasing the rate, we're increasing it for both of the reactions, the forward and the reverse. So our overall effect will just cancel out. And using a homogeneous catalyst will not have an effect in the sense of increasing our equilibrium yield of chloroethene because it will affect both the forward and the reverse reactions, so it will not favour one reaction over the other. But increasing our temperature will favour our forward reaction, and this is because our forward reaction is endothermic. So if we increase the temperature of our system, then this will be absorbed by the forward reaction and decrease the temperature back down again. It will restore that equilibrium with the conditions. Therefore, we will get that increased equilibrium yield of chloroethene, so our answer is going to be C. This table below shows some enthalpy changes of formation values. And we need to use these to identify the value for the enthalpy change of reaction for this reaction shown below. So we've got the reaction of titanium chloride with water to form titanium oxide and some hydrogen chloride gas. So we can't work out this enthalpy change of reaction directly. Therefore, we need to use a Hess cycle in order to calculate this indirectly using enthalpy change of formation values given to us. So Hess's law states that the enthalpy change of reaction is the same irrespective of the route taken, so whether you go directly from A to B or via the series of other reactions. In this case, we're going to be using our enthalpy change of formation reactions. So let's start by forming our Hess cycle. So I'm just going to rewrite out the reaction here so we've got a bit more space, like so. And because we're using enthalpy change of formation values, that means that we're forming each of these compounds. So on the bottom here, we need to write out the elements which we're forming them from. And this is just so that we can identify which way round our cycle is going to go, so that we add and subtract things the correct way. So we don't need to worry about balancing these elements because we're just using these to show the correct direction of our arrows. So the arrows are going upwards because we're forming these compounds above from these elements below. So we're starting from here and we're forming these things. And then I'm just going to label each of these reactions. I'm just going to label them as enthalpy changes 1, 2, and 3. You can label them any way you want or any different way you want. And now let's do our Hess cycle calculation. So with our Hess cycles, our clockwise arrows are equal to the anti-clockwise arrows. And if I just slightly bend these arrows a bit, what we can see is that enthalpy changes 1 and 2 are going in the same direction, they're going clockwise, and enthalpy change 3 is going in the opposite direction, that's going anti-clockwise. So we started to form our equation now, and we can work out enthalpy changes 2 and 3 from our table, and we use this to work out what enthalpy change 1 is, our enthalpy change of reaction. So therefore we can rearrange our equation for our enthalpy change 1. So now let's start to plug in some numbers from the table. So from our enthalpy change 3 to start, we've got our enthalpy change of formation of that titanium oxide plus 4 lots of the enthalpy change of formation of our hydrogen chloride. So we need to include our molar values for the things which we're forming. And then we're going to subtract the enthalpy change of formation of the titanium chloride plus 2 lots of the enthalpy change of formation of water. Now we need to be quite careful here with our brackets if we're going to put all of this in our calculator together, because the calculators often get the double negatives a bit muddled up if we haven't bracketed it up. So I've been quite careful here with how many brackets I've put in. And if we work out each of these large square brackets individually, what we get is for the first one, so our enthalpy change 3, we get a value of negative 1,313. And then we're subtracting enthalpy change 2, which comes to negative 1,376. So overall, we get a value of plus 63 kilojoules per mole. And this matches up with option D, so that's going to be our answer. We're told that zinc reacts with copper sulfate solution, and we need to determine which apparatus can be used to determine the effect of the concentration of copper sulfate on the rate of reaction. So let's start by writing out a reaction equation so that we can see what sort of reaction we've got. So we have zinc metal reacting with copper sulfate solution, and this is going to be a displacement reaction. So our zinc is going to displace that copper from the solution. So we will then get zinc sulfate solution and copper metal. And the reason why we get this displacement is because the zinc is more reactive than the copper, therefore it displaces that copper out of the solution. So looking at our equation here and matching this up to our options, what we can see straight away is that we don't have an acid-base reaction. So we don't have a proton donor or a proton acceptor. Therefore, using a pH meter will not help us to determine the effect of the concentration of copper sulfate on our rate of reaction, because we're not going to be getting any significant changes of pH in this reaction. Now, as well as this, we're also not producing any gases. So we've started with a solid in solution and we're producing a solid in solution. So we're not going to produce any gases, therefore a gas syringe would not be an appropriate piece of equipment to use here. And because we're not producing any gases, which can then be released, we're also not going to see any change in mass in this reaction, because nothing is going to be able to escape our system. Therefore, we can't use a balance. So this leaves a colorimeter as our answer, which is also appropriate for this reaction because our copper sulfate is a blue solution because our copper is a transition metal, and we know that a property of our transition metals is that they produce coloured solutions for their compounds, whereas our zinc is not a transition metal. Therefore, the zinc sulfate solution is actually just going to be colourless there. So what we will see as this reaction proceeds is we'll see the blue colour fading out. Therefore, the colorimeter will be the most appropriate piece of apparatus to determine our effective concentration. The boiling point of hydrogen bromide is minus 67 degrees centigrade, and the boiling point of hydrogen iodide is minus 34 degrees centigrade. And we can explain the difference in these boiling points down to the strength of the bonds or interactions. And for this question, we need to identify which bonds or interactions are responsible for the higher boiling point of hydrogen iodide. So hydrogen bromide and hydrogen iodide are both non-metal based compounds, and we know the formula of each of these as HBr for hydrogen bromide and HI for hydrogen iodide. And this is because for both of these we've got a simple molecular structure. And this is where we've got strong covalent bonds within the molecule. So for example, between the hydrogen and the bromine, we've got a covalent bond, or between the hydrogen and the iodine. But between the different molecules, we've got weak intermolecular forces. Therefore, when we want to boil our molecules, we're going to be separating them out. So we're going to be overcoming the intermolecular forces of attractions to do that. Therefore, our answer can't be A, because when we're boiling our compounds, we're not breaking the covalent bonds, we're just separating out the different molecules. Now, we've got hydrogen bromide and hydrogen iodide, and neither the bromine nor the iodine is electronegative enough to form hydrogen bonds. Therefore, we can eliminate option B. And what we do know is that both of these compounds have permanent dipole-dipole and induced dipole-dipole interactions. But our iodine is further down in group 7, therefore it's got weaker permanent dipole-dipole interactions, which does not explain why it's got a higher boiling point than hydrogen bromide. If it's got weaker permanent dipole-dipole interactions, we would expect it to have a lower boiling point, so it requires less energy to overcome. Therefore, it must be our induced dipole-dipole interactions that explain why we've got a higher boiling point. And it's because the iodine is further down in the periodic table, therefore it's got a larger number of electrons, hence it's got stronger induced dipole-dipole interactions between the molecules. The first 8 successive ionization energies in kilojoules per mole of an element in period 3 are shown below. And for this question, we need to identify what element this belongs to. So we've been given these values for our ionization energies, and recalling that ionization energies are the energy required to remove an electron from our species, and we've got the first to the 8th here. So these going from left to right are going to be the energy required to remove the first, the second, the third, the 4th electron, and so on and so forth from our element. So what we're looking for in this set of numbers is where there is a big jump in values, because this represents going from an outer shell to an inner shell, and there'll be a big jump, so we'll see a big increase in our values, because as we move to an electron shell that's closer to the nucleus, the electrons will be more strongly held there by the nucleus, therefore will require more energy to remove it. So working our way along, we can see a big jump between the values of 6,274 to 21,269. So that is the big jump that we can see from these values. So we're looking for more than just the regular pattern. So the first 5 ones here, although they are increasing, they're increasing in a steady amount, whereas this is where we're seeing a huge increase. And then because this represents the removal of 5 electrons, that must mean that this is an element with 5 electrons in the outer shell. So we can refer to our periodic table again and look for the element out of each of these that's also in group 5 or 15, and that corresponds to phosphorus. So our answer is going to be C. Using the graph, what is the value of the pre-exponential factor A for the decomposition of N2O5? So we've got our equation here for the decomposition, and here we've got a graph where we've got ln K plotted on the y-axis and 1 over T plotted on the x-axis. And with these values, and noting that we need to work out the pre-exponential factor, we know that this is going to be a graph of the Arrhenius equation in linear form, which is in your data sheet, and the equation is ln K equals negative activation energy divided by the gas constant R and the temperature plus ln A. And linking this to our y equals mx plus c equation for a straight line, we can see that ln A is going to be equal to the y-intercept of this graph. So the y-intercept of this graph is at 31.5. So we can read this off from the graph, and that's at 31.5. So that means that ln A is going to be 31.5, but we just need to work out what the value of A is. So to work that out, we do e to the power of our value, and that cancels out the ln. So A is going to be equal to e to the power of 31.5, which in your calculator will give a value of 4.79 times 10 to the 13, and that's in units of seconds to the minus 1. Therefore, our answer is going to be D. A solution of propanoic acid, with the formula shown here, has a pH of 2.89 at 25 degrees centigrade. And for this question, we need to work out what the concentration of our H plus ions are in this solution. So the square brackets represent concentration. So we know that to work out pH, we take the negative log to the base 10 of the concentration of our H plus ions. Therefore, if we want to work out the concentration of the H plus ions, we have to do 10, so our base, to the power of negative pH. So for this question, we were told our pH is 2.89, so we do 10 to the power of negative 2.89. And this gives a value in the calculator of 1.288 to 3 decimal places times 10 to the minus 3 moles per decimeter cubed. And this rounds to 1.3 times 10 to the minus 3 moles per decimeter cubed, which matches up with option C. The lattice enthalpy of calcium chloride can be calculated using 3 of the enthalpy changes shown below. And for this question, we need to identify which enthalpy change is not required. So the 4 options we have here are the enthalpy change of solution of calcium chloride, the enthalpy change of hydration of the chloride ions, the enthalpy change of formation of the calcium chloride, and the enthalpy change of hydration of the calcium ions. So there are a couple different ways that we can work out the lattice enthalpy of our ionic compound, and that's by using either a larger Born-Haber cycle or by using our solution hydration Born-Haber cycle. So the larger Born-Haber cycle involves formation enthalpies, atomization enthalpies, ionization enthalpies, electron affinities, and so on and so forth. But here we can see that we've got the data for the enthalpy change of solution of our compound and then the hydrations of the respective ions. So if I just draw out what a cycle would look like, then we can see which enthalpy change we do not need. So for our lattice enthalpy, that's forming our solid ionic compound from the gaseous ions. So I'll put our solid calcium chloride here, and then the gaseous ions at the top. And this here is going to be our lattice enthalpy, and that's always exothermic, so I've drawn a downwards arrow. Then our enthalpy change of solution is if we go from the solid calcium chloride and we dissolve that in water to get the aqueous compound here. Now, these can be exothermic or endothermic, so I'm just going to do a downwards arrow for the purpose of this diagram. So this is our enthalpy change of the solution for the calcium chloride. So then just to finish off this cycle, all we actually need is just going to be the hydration values of the ions. So that's where we go from the gaseous ions to the aqueous solution. So we're hydrating the ions with the water. So this is our hydration enthalpy. And then what we can see from this cycle is that we don't actually need the enthalpy change of formation of calcium chloride in order to work out this lattice enthalpy, because we've not got our calcium and our chlorine in elemental form in order to form that solid. Therefore, our answer is going to be C. Which redox reaction contains the largest change in oxidation state for sulfur? We've got 4 different equations below, so let's work out the oxidation states for the sulfur in each of these equations. So starting with equation A, we can see that our sulfuric acid here, we've got 4 lots of the oxygen, which at -2 for each oxygen, that gives -8 for that part. And then we've got 2 lots of +1 for the hydrogen, which gives +2. Therefore, to have a neutral compound overall, the sulfur will have to be oxidation state +6 there. And then on the right-hand side, with our sulfur-containing compound, we've got 2 lots of +1 again from the hydrogen. Therefore, the sulfur will have to be in oxidation state of -2 for this compound. So we're going from +6 to -2, so that is a change of -8. So in equation B, our sulfur will just have an oxidation state of 0 because it's in its elemental form. And then on the right-hand side with the sulfur dioxide, we've got 2 lots of -2 from the oxygen giving -4. Therefore, the sulfur will need to be in oxidation state +4. So our change with this one is going to be +4. For equation C, we've got, again, 3 lots of the -2 for the oxygen, giving -6, but we need to have a -2 charge overall. Therefore, the sulfurs need to add up to +4, so individually the sulfur will have an oxidation state of +2 there. And then on the right-hand side, we've got 2 different sulfur-containing compounds. So our elemental sulfur, we know, has an oxidation state of 0. And then our sulfur dioxide, we worked out above, that will have an oxidation state for the sulfur of +4. So our biggest change here is just a change of 2. So we've got a change of -2 and a change of +2 there. So let's look at the last equation now. So again, we've got our elemental sulfur on the left, that's got oxidation state of 0. And then on the right, we've got that sulfuric acid again, where we worked out above that our sulfur has got an oxidation state of +6. Therefore, our change here is +6. So we can see overall that the biggest change in oxidation state is going to be from equation A, where we had a change of -8. So our answer will be A. The following compounds exist in equilibrium with the equation here shown below. At room temperature and pressure, the equilibrium lies well to the right-hand side. For this question, we have to deduce which of the following values could be the equilibrium constant by using all of this information here. So let's start by jotting down an equation for the equilibrium constant. So if we had a Kc, for example, then our equilibrium constant is equal to the concentration of the products divided by our reactants. Remembering that if we have any mole values in front in the equation, then this is going to be the indice within our Kc equation. So here we're squaring some of these values because they've got a big 2 in front. So this is going to be our Kc equation. Now, if our equilibrium constant was roughly in the middle, then that will mean that we've got equal quantities on the top and on the bottom of our equation, which means that we will get a value close to 1. So that is if it is equal. Now, if our equilibrium lies to the left-hand side, we would expect a value of less than 1. So we're looking for standard form with negative indices. Or if we're looking for an equilibrium which lies to the right-hand side, we're going to be looking for a value that's much greater than 1. And that's because we will have more of the products on top in our fraction, therefore we will get a larger value for Kc. So out of our values here, our answer could either be B or D, because these are the values which are much greater than 1. So to determine which is which, we've just got to look at the units now. So the units for concentration are moles per decimeter cubed. So on top, we've got moles per decimeter cubed effectively cubed, and then on the bottom, we've got our moles per decimeter cubed to the power of 4. So overall, we can cancel out the top and we can cancel out 3 from the bottom, which just gives us a moles per decimeter cubed on the bottom. So when we bring that up to the top, you change the signs. So our units are going to be mole to the power of -1, because we flipped it from 1 to -1, and then decimeters cubed. And this matches up with D. So our answer is going to be D. Copper-2 ions form an aqueous complex ion X with chloride ions. Which statement about X is true? X has optical isomers, X has a square planar shape, X has the formula CuCl4 2+, or X has a yellow colour. So this complex here is one which you need to learn as part of the course, and you need to learn that it is a tetrahedral complex because we've got 4 chloride ions acting as ligands with this copper-2+. So overall, if we've got a copper-2+, and then we've got 4 chloride ions, we know that chloride ions have got a charge of -1 each. Therefore, our overall charge is going to be a 2-. So this eliminates option C from our table. And then, as I mentioned, you need to learn that this is actually a tetrahedral shape for this complex. Therefore, our answer can't be B. And because it's tetrahedral and we've got 4 of the same ligand bonded to our central copper ion metal, we also can't have optical isomers for this complex. Therefore, our answer is going to be D, that X has a yellow colour, and this is also something which you need to learn as part of this complex ion. So our answer is D. 2 tests are carried out on an aqueous solution of copper-2 sulfate, with the formula shown here. Test 1 is the addition of potassium iodide solution, and test 2 is the addition of barium chloride solution. And for this question, we have to pick which of the following statements are true. So it could either be just one that's true or a combination of the three statements. So let's think about what happens during each of these tests. So these are some of the test tube reactions that you need to learn. So these are some recall style questions here. So the first one to think about is going to be our addition of barium chloride solutions. This is test 2, and we use this to test for sulfate ions, which we have in our copper sulfate compound, and therefore we will see the positive test, which is the production of a white precipitate, which is a barium sulfate solid there. So that means that statement 2 is definitely correct. So from our options A, B, C and D, we can eliminate option D so far. So now let's have a think about what observations we will see for test 1. So test 1 is the addition of potassium iodide solution. And what we will get is the reaction of the iodide ions with the copper 2+ ions from these solutions. This is another recall reaction, and this is going to be a redox reaction. And reaction will be as follows. This is the ionic equation. So we have our copper 2+ ions in solution reacting with the iodide ions from the potassium iodide solution. And from this, we produce copper iodide solid and iodine solution. So just balancing this up, we're going to need to balance the charges and the oxidation states. So we have a neutral charge on the right-hand side. We currently have a 1+ charge on the left-hand side. We can also see that we've got 3 iodines on the right and 1 on the left, but if we put a 3 in front of this iodide ion here, this will still not give us balanced charges. So we're going to need to do something with the coppers in order to balance this out. So if I put a 2 in front of the copper 2+, and therefore a 2 in front of the copper iodide, because those coppers have got to be equal, then now I can put a 4 in front of the iodides. So this means we've got 4 iodine atoms either side, and then our charges will be neutral on the right again, and then we've got 4+ from the coppers, we've got 4- from the iodides, so therefore we've got neutral overall on the left-hand side now. And colour-wise, this is producing an off-white precipitate, so that's our copper iodide. And then the brown solution is the iodine solution. So that means that statement 1 is also correct. So now we can eliminate option C. So the last one to figure out is whether statement 3 is correct as well. So we've already said that our test 1 is a redox reaction, but let's have a think about whether test 2 is a redox reaction as well. So test 2, we've got the reaction of our barium 2+ ions in solution with the sulfate ions in solution to produce that white barium sulfate precipitate, but we haven't got any change in oxidation states in these ions or compounds. Therefore, test 2 is not going to be a redox reaction. Therefore, statement 3 is incorrect, so our answer is going to be B. Two students set up the equilibrium system shown below. The students then titrated samples of the equilibrium mixture with sodium hydroxide in order to determine the concentration of the ethanoic acid. These results were then used to calculate a value for Kc, but they got different values for Kc each. Which of the reasons below could explain why the values for Kc were different? Each student carried out their experiment at a different temperature. Each student used a different concentration of sodium hydroxide in their titration. Each student titrated a different volume of the equilibrium mixture. And our answer could either be one or a mixture of each of these options. So the key thing with Kc, our equilibrium constant, is that it is only affected by temperature and changes in temperature. So that means that option 1 will definitely be correct, and this eliminates C from our answers. Now thinking about options 2 and 3, option 2, each student used a different concentration of sodium hydroxide in their titration. This won't make a difference because although they might have different concentrations, this will therefore affect the volume of sodium hydroxide, which is needed, so it ends up balancing out to be the same amount of moles due to the equation of moles equals volume times by concentration. So by keeping the equilibrium mixture the same, even if we affect the concentration of the sodium hydroxide, for example, if we used a more concentrated version of sodium hydroxide, you would therefore need a smaller volume in order to react the same amount of moles with the equilibrium mixture. So this one will not give different values for Kc. So from this we can actually eliminate A and B, leaving our answer to be D, but let's just confirm this as well by checking option 3. So this is a similar idea here. Each student titrated a different volume of the equilibrium mixture. And if you use a different volume of the equilibrium mixture, this gets balanced out because you will then need a different volume of sodium hydroxide, but you will still have the same amount in moles reacting together. So this won't affect the overall value for Kc. Therefore, our answer is D.
Ammonia is a gas with covalently bonded molecules consisting of nitrogen and hydrogen atoms. Part A. Show the electron configuration of a nitrogen atom using electron-in-box diagrams. Label each subshell. The order for which subshells fill, or in the electron configuration how subshells fill, is 1s, 2s, 2p. Nitrogen's in group 5. And it's going to have the electron configuration of 1s2, 2s2, 2p3. So filling our orbitals will have 2 electrons with opposite spin, that's the 2 half arrows going in opposite directions, and that's because electrons repel each other, so they're not going to go in the same direction, they're going to go in opposite directions. Our 2s2, and then we're going to have our 2p3. And how I filled this is using something called Hund's rule. And Hund's rule says that it's more stable to fill each orbital with 1 electron than it is to fill it with 2, and that limits repulsion. To get the 2 marks for this question, you get a mark for having your correct subshells, so your 2s and 2p, and then you get a mark for correctly filling your subshells with your electrons. Part B. Ammonia can be made from the reaction of nitrogen and hydrogen in the Haber process. N2 plus 3H2 with an equilibrium arrow, an Fe catalyst at 450 degrees Celsius and 200 kilopascals creates 2NH3, and the enthalpy is minus 92 kilojoules per mole. What effect will increasing the temperature have on the composition of the equilibrium mixture and on the value of the equilibrium constant? Explain your answer. So, firstly, we need to look at the effect on increasing temperature. So, increasing temperature, we need to look at if the equilibrium is exo or endothermic in the forwards direction. And the forwards reaction is exothermic. We know this because our delta H, or our enthalpy value, is negative. If it was positive, it would be endothermic, but it's negative, so it's exothermic. And that means if we increase the temperature, the reaction is going to favour the backwards reaction, or the endothermic direction. And if it's favouring the endothermic direction or the backwards direction, that means we're going to produce more N2 and H2. And if we produce more N2 and H2, that means that our value of the equilibrium constant will decrease. So here we've answered both parts of this question in one sentence. So it doesn't require a lot of writing to get both marks. So the reason why the equilibrium constant decreases is because the equilibrium constant will be Kc NH3 squared over N2 multiplied by H2 cubed. So if our N2 and our H2 are increasing, that is going to mean that our value of NH3 will be decreasing, and so Kc will also decrease. To get the marks for this question, you get 1 mark for saying that the forward reaction is exothermic, so increasing temperature favours the backwards reaction. That gets you your first mark. And then your second mark comes from saying that more N2 and H2 will be produced, and so the value of the equilibrium constant will decrease. Part C. A chemist mixes together 0.450 moles of N2 with 0.45 moles of H2 in a sealed container. The mixture is heated and allowed to reach equilibrium. At equilibrium, the mixture contains 0.400 moles of N2 and the total pressure is 500 kilopascals. Calculate Kp. Show all your working. Include units in your answer. Firstly, let's write an expression for Kp. So Kp equals the partial pressure of NH3 squared divided by the partial pressure of N2 multiplied by the partial pressure of H2 cubed. So what I've done, if we look at the equation or the equilibrium, I have taken the stoichiometry and I've raised that as the power, and we've got kind of products over reactants if we look at the forwards reaction. So then we need to work out the number of moles that we have at equilibrium. We've got the number of moles of N2 and the initial moles of N2 and H2. So we can work out the moles of equilibrium of H2 and NH3. So if we do an ICE calculation, we have N2, H2, NH3. Our N2 initially will be 0.450 and so will our H2. And initially we will have no ammonia. Then the change, well, we know that we've got 0.400 moles of N2 at equilibrium, and that's a change of 0.050. Then we look at the stoichiometry. So for our H2, that will be minus 0.150, and that's 0.300. And then for ammonia, it will be the opposite change, but the same ratio. So we'll have plus 0.100. So we get 0.100 moles. And this is all in moles. Then we need to work out the partial pressure. So partial pressure is the molar ratio multiplied by the total pressure. So if we start with working out the partial pressure of N2, so the partial pressure of NH2 is going to equal 0.400 divided by 0.800, that's our mole fraction, times by 500 because that is our total pressure, 500 kilojoules. That equals 250 kilopascals. Then we're going to do the same for H2, and that equals 0.300 divided by 0.800 multiplied by 500, which gives us 187.5 kilopascals. And finally, the partial pressure of NH3, that is 0.100 divided by 0.800 multiplied by 500, and that gives us 62.5 kilopascals. So finally, working out Kp, we're going to plug these numbers into our expression for Kp. So that is 62.5 squared divided by 250 multiplied by 187.5 cubed, which gives us 2.37 times 10 to the minus 6 kilopascals to the minus 2. How I worked out the units, well, we have kilopascals squared divided by kilopascals times kilopascals cubed. So that's kilopascals squared over kilopascals to the power of 4. So we can cancel the top and then cancel 2 from the bottom, and that's 1 over kilopascals squared, which is kilopascals to the minus 2. So writing this in the answer line, we have 2.37 times 10 to the minus 6 kilopascals to the minus 2. To get the marks for this question, you get a mark for working out the moles of H2 and NH3 in equilibrium. You get a mark for working out all the partial pressures correctly. You get a mark for plugging your partial pressures into a correct expression for Kp. And then you get a mark for finding 2.37 times 10 to the negative 6. And a mark for the correct units, so kilopascals to the negative 2. Part D. A chemical company receives an order to supply 1.96 times 10 to the 10 decimeters cubed of ammonia at room temperature and pressure. The Haber process produces a 95.0% yield. Calculate the mass of hydrogen in tons required to produce the ammonia. Give your answer to 3 significant figures. Firstly, let's highlight the key pieces of information. Our first key piece of information is that we produce 1.96 times 10 to the 10 decimeters cubed of ammonia at room temperature and pressure, and that the Haber process produces a 95% yield. We're asked to calculate the mass of hydrogen in tons required to produce the ammonia, and we need to give our answer to 3 significant figures. Because of the information, we know that we can use the equation number of moles equals the volume divided by the molar volume, which is 24 decimeters cubed if the volume is decimeters cubed. So, using the volume that we've been given, we can do the number of moles of NH3 equals 1.96 times 10 to the 10 divided by 24, and that equals 8.167 times 10 to the 8 moles. And then using the equation triangle of mass divided by moles times relative formula mass, well, then we can work out hydrogen after we've scaled the moles. So the equation is N2 plus 3H2 goes to NH3, or 2NH3. And we're looking for the moles of hydrogen. So scaling our moles, we would do 8.167 times 10 to the 8 divided by 2 multiplied by 3. And that equals 1.225 times 10 to the 9 moles. Using the equation triangle, well, the relative formula mass of hydrogen is 1 times 2, which is 2. So then we do the moles, which is 1.225 times 10 to the 9 multiplied by 2, and that equals 2.450 times 10 to the 9 grams. But we're asked for mass in tons, so we need to do 2.450 times 10 to the 9 divided by 1 times 10 to the 6, which is tons in grams. So that equals 2,450 tons of H2. And then finally we need to work out how much we need to get a 95% yield, because this is if it was 100% yield, so we need slightly more. And so working out the mass that we need for a 95% yield, we do 2,450 multiplied by 100 divided by 95. And that will give us 2,580 tons, which we can then write on the answer line, 2,580. And that is to 3 significant figures, which is what the question has asked us to give our answer to. To get the 3 marks for this question, you get a mark for working out your moles of hydrogen, which is your 1.225 times 10 to the 9. That's your moles of hydrogen. And then you get a mark for working out the mass in tons of hydrogen, so 2,450 tons, and then a mark for working out the mass in tons that you need for a 95% yield, which is 2,580 tons. Part E. Part 1. Hydrazine, N2H4, is used as a rocket fuel. Hydrazine can be prepared from the reaction of ammonia with sodium chlorate 1. There are 2 other products in the reaction. Write an equation for this reaction. So firstly, let's write our reactants. We've got NH3 plus NaOCl. That's our sodium chlorate and our ammonia. And that's going to produce hydrazine, which is N2H4. We're also going to produce sodium chloride, or NaCl. And then our second product will be water, or H2O. Balancing this equation, we need 2 ammonias, and then our equation is balanced. To get the mark for this question, you need to have the full correct balanced equation for this reaction. Part 2. Using the electron pair repulsion theory, draw a 3D diagram for a molecule of hydrazine. Predict the HNH bond angle around each nitrogen atom. Okay, firstly drawing the structure of hydrazine. We have N connected to an N, or bonded to an N, and then we have 2 hydrogens attached to each nitrogen. So that will be like this. And then we're going to have a lone pair on each nitrogen. So looking at the electron pair geometry, well, we've got 3 bonding pairs attached to each nitrogen and 1 lone pair. So 3 bonded pairs, 1 lone pair. That means we're going to have pyramidal shapes, and a pyramidal shape has a bond angle of 107 degrees. To get the marks for this question, you get a mark for drawing the correct structure of hydrazine, as I've drawn here, and then you get a mark for stating the correct bond angle of 107 degrees. Iodine monochloride, ICl, can react with hydrogen to form iodine. This reaction was carried out several times using different concentrations of ICl or H2. The initial rate of each experiment was calculated and the results are shown below. Initial concentrations are shown for each experiment. Part A, Part 1. Calculate the rate constant K for this reaction. Include units in your answer and show all your working. The key in this question is that we're working out rate constant. For rate constant, the general rate equation we can use to work out the rate constant K, because it's rate K and then concentration of your reactants raised to whatever the order of reaction with respect to the concentration of your reactants is. So if it was 0 order, X would be 0 or Y would be 0. If it was first order, X or Y would be 1, and if it was second order, X or Y would be 2. So using this, we can work out the rate equation for this reaction, and then we can work out K. So our reactants are ICl and H2, so our rate equation is going to be rate equals K ICl raised to the power of something, H2 raised to the power of something. So the way you work out the order of reaction with respect to the concentration of one of your reactants is where the other one remains constant, or the concentration remains constant, and then the other one is changing. So here we've got our H2 remaining constant and our ICl is increasing by a factor of 2, or it's doubling. And then you look at the rate and how this has affected it. And what's happened to the rate is it's increased by 2 as well, it's doubled. And that means it's going to be first order, because it's the same change. If it was second order, it would be the rate is increasing by 2 squared, or times 4. And if it was 0 order, the rate would stay the same and it wouldn't matter how concentration changes, because it would have no effect on the rate, and that's what a 0 order reaction is. So now we've worked out our order of reaction with respect to the concentration of ICl, we can now work out the order of reaction with respect to the concentration of H2. So we don't have an experiment where the concentration of ICl stays the same, but we do have the fact that we know that ICl is first order. So here in experiment 2 to 3, where we've divided by 4, and we have divided H2 by 2, and the rate is then divided by 8. So we can use this information and the fact that ICl is first order to work out the order with respect to the concentration of H2. So the way that order's worked out, and if we looked at it a different way, in experiment 1 to 2, we've multiplied by 1. And then if you look at the times 2 and the times 1, if you do 2 times 1, that's going to be your timesing factor, which is 2 here. And then we've got a divide by 4 and a divide by 2. 4 times 2 is 8, so we're dividing by 8, and that's if it's first order, which it is, because this matches 4 times 2 is equal to 8. And that means our order with respect to the concentration of H2 is first order. So we could rewrite this as rate equals K, concentration of ICl, multiplied by the concentration of H2. And then using the data in experiment 1, we can work out K, because K will be equal to rate divided by the concentration of ICl multiplied by the concentration of H2. So, using experiment 1, K is equal to 2.04 times 10 to the negative 2 divided by 0.250 times 0.500. And that gives us a K value of 0.163, which we can then write on the answer line. Now, working out units, we have moles, decimeters to the minus 3, seconds to the minus 1 as our rate units. And then we have moles squared, decimeters to the minus 9 on the bottom. And that is our two concentrations, because we've done moles per decimeter cubed squared. And that gives us moles squared, decimeters to the minus 9. So we can eliminate one of the moles and one of the decimeters cubed. And that's going to give us a unit of moles to the minus 1, decimeters cubed, seconds to the minus 1. And this is how you answer the question. To get the 4 marks for this question, you get a mark for working out the orders of reaction with respect to the concentration of ICl and with respect to the concentration of H2, which are both first order. You get a mark for working out the rate equation. You get a mark for correctly working out K, and a mark for correctly working out the units of K. Part 2. Calculate the rate of reaction when ICl has a concentration of 3.00 times 10 to the negative 3 moles per decimeter cubed, and H2 has a concentration of 2.00 times 10 to the negative 3 moles per decimeter cubed. Show all your working. We know from the previous question that the rate equation is rate equals 0.163 concentration of ICl multiplied by the concentration of H2. And our 0.163, that's our K value. So then we can plug in the concentrations of ICl, which is 3 times 10 to the negative 3 moles per decimeter cubed, and H2, which is 2 times 10 to the negative 3 moles per decimeter cubed, and work out our rate. So that's going to be rate equals 0.163 multiplied by 3 times 10 to the negative 3 times 2 times 10 to the negative 3, and that equals 9.78 times 10 to the negative 7 moles per decimeter cubed seconds to the minus 1, which we can then write on the answer line provided. To get the mark for this question, you must write 9.78 times 10 to the negative 7 on the answer line provided. Part B. Reaction rates can be increased or decreased by changing the temperature of the reaction. Figure 17.1 below shows the energy distribution of the reactant molecules at 25 degrees Celsius. Draw a second curve on figure 17.1 to represent the distribution of the same number of molecules at a higher temperature. Use your curve to explain how increasing the temperature increases the rate of reaction. So the new line for a higher temperature is going to be a lower peak, and it's going to tail off earlier. And then we can show activation energy and shade in the fact that we've got more molecules, because here I'm shading the number of molecules with an energy above the activation energy at 25 degrees Celsius, but we can see at our higher temperature that we've got a lot more molecules with an energy higher than the activation energy, which is what we can write about explaining how increasing the temperature increases the rate of reaction. So how we explain how increasing the temperature increases the rate of reaction is that the graph shows a higher temperature, there's more molecules that have an energy above the activation energy. To get the 2 marks for this question, you must have the correct graph drawn. So you need to have something with a lower peak and then show that the activation energy on the graph, and then write this statement below. A student is asked to calculate delta H at 25 degrees Celsius for the combustion of butan-1-ol. The teacher provides 2 pieces of information: the equation for the combustion of butan-1-ol, standard entropies of butan-1-ol, oxygen, carbon dioxide and water. The student carries out an experiment using the apparatus below and obtains the following results. The specific heat capacity of water is 4.18 joules per gram per Kelvin. Use the information on the previous page to calculate delta G in kilojoules per mole for the combustion of butan-1-ol according to equation 2 at 25 degrees Celsius. Show all your working. Firstly, let's highlight the key pieces of information. Our first key piece of information is equation 2. And then our second key piece of information is our standard entropies of butan-1-ol, oxygen, carbon dioxide and water. Also, the specific heat capacity of water and the volume of water that we're using in this experiment. Then the experimental data, specifically the initial and the maximum temperature, are going to be really important in our first step, and then the masses of the burner before burning and after burning are going to be useful in our second step. And then we need to note that we're working out delta G in kilojoules per mole. Firstly, let's work out the energy, or Q, in joules and then convert to kilojoules per mole. and Q equals mc delta T. So we can work out Q because we've got the mass of water is 100 centimetres cubed or 100 grams. And then we're going to multiply by 4.18, which is the specific heat capacity of water, or C, and then multiply by delta T, which is equal to 39 minus 18.5. And that's going to give us a Q value of 8,569 joules, and that equals 8.569 kilojoules. Using the equation triangle of mass divided by moles times relative formula mass, we can work out the moles of butan-1-ol. But first, working out its mass, we're going to need the information in the table here, and we're going to minus the two masses. So it's going to be 98.997 minus 98.738. And that is equal to 0.259 grams of butan-1-ol. And then we're going to work out the relative formula mass of butan-1-ol, which is going to be 12 times 4 plus 10 plus 16, which is equal to 74 grams per mole. And then using the equation triangle, we can do 0.259 divided by 74, and that is equal to 3.5 times 10 to the negative 3 moles of butan-1-ol, which we can then use later on in the question. So the next part is working out delta S, because in order to work out delta G, we need the equation delta G equals delta H minus T delta S. And delta S is the change in entropies. And it has the equation of delta S equals delta S of products minus the delta S of reactants. So this is going to be equal, or our delta S is going to be equal to 4 times 214 plus 5 times 70 minus 228 plus 6 times 205. And that gives us a delta S value of minus 252 joules per Kelvin per mole, which can then be converted to kilojoules per Kelvin per mole, and that would be minus 0.252 kilojoules per Kelvin per mole. And now, working out delta G with all the information, we need delta H. And we can work out delta H using our Q value of energy and our moles. So delta H is equal to 8.569 divided by 3.5 times 10 to the negative 3, and that equals minus 2,448 kilojoules per mole. So then delta G is going to be minus 2,448 minus 298 times minus 0.252, and that equals minus 2,373 kilojoules per mole, which we can then write on the answer line provided. To get the 7 marks in this question, you get a mark for working out Q, you get a mark for working out your moles of butan-1-ol, you get a mark for working out your delta H, which I've written here as minus 2,448. I've added the minus because it's a combustion reaction and that's exothermic. And then you get a mark for working out that delta S is your delta SP, or your change in enthalpy of products, minus your change in enthalpy of reactants. And then you get a mark for working out that that is minus 0.252. you get a mark for working out your Gibbs free energy or your delta G. The first mark comes from just stating the equation and plugging the numbers in. Then your second mark comes from your correct typing in of the calculator and getting minus 2,373 kilojoules per mole. This question is about the chemistry of the elements in group 2 and the halogens. Part A. A student prepares an aqueous solution of magnesium chloride by reacting magnesium with excess hydrochloric acid. Write an equation including state symbols for this reaction and state the observation or observations the student should make whilst carrying out this experiment. Firstly, we're going to write the equation with the state symbols. So our equation, we're preparing magnesium chloride, which has the formula MgCl2, and we're reacting magnesium with excess hydrochloric acid. So our equation, we're going to have Mg, or magnesium, which is a solid, with hydrochloric acid, which is aqueous, and we're going to produce magnesium chloride, so MgCl2, which is aqueous also. And then we're also going to produce a hydrogen gas. And finally, we need to balance the equation by adding a 2 in front of our hydrochloric acid. In terms of the observations, because we've got gas produced, we're going to see some effervescence. But we need to say our second observation is that the solid is going to dissolve, the solid in this case being magnesium. To get the mark for this question, or the 2 marks, you get 1 mark for the correct equation and 1 mark for both observations, so you need to have both to get the mark. Part B. Lattice enthalpies give an indication of the strength of ionic bonding. How would the lattice enthalpies of magnesium chloride and calcium chloride differ? Explain your answer. This question consists of 3 parts in order to get the 3 marks for this question. So the first reason why the lattice enthalpies of magnesium chloride and calcium chloride differ is because magnesium chloride has a more exothermic lattice enthalpy than calcium chloride. So this statement gets you your first mark for this question. And then your second reason or mark is because magnesium 2+ as the ion is smaller than calcium 2+, and so for your third mark, the attraction between magnesium 2+ and Cl- or chlorine minus is greater, so this gets you your third mark. So the breakdown for marks is first stating that the magnesium chloride lattice enthalpy is more exothermic, your second mark from saying that magnesium 2+ ion is smaller, and then your third mark is from saying that the attraction is greater between magnesium and chloride ions. Part C. The table below shows the enthalpy changes that are needed to determine the lattice enthalpy of magnesium chloride. Part 1. On the cycle below, write the correct letter in each box. Okay, let's start with this arrow. So what's happening is magnesium plus gas is going to magnesium 2+ gas. So what this is called is the second ionization energy of magnesium, which is here, and so we can label this as F. Then we can look at the next arrow below, and what's happening is magnesium gas is going to magnesium plus gas, which is the first ionization energy of magnesium, and so we can label this B. Then if we continue down and look at this arrow, what's happening is magnesium solid is going to magnesium gas, and that's called the atomization energy of magnesium, which is E, and so we can label this E. Then looking at the next arrow down, we've got magnesium solid and chlorine gas going to magnesium chloride. So these are the elements in their natural forms going to this compound, And what that is the formation of magnesium chloride, which is D, so we can label this D. And finally, looking at the arrow on the right, well, we've got our ions of magnesium and chlorine, and we're forming our magnesium chloride. And what this is called is the lattice enthalpy of magnesium chloride. So that's letter G, so we can label this as G. To get the 3 marks for this question, you must have all 5 letters correct. If you have 4 correct, you get 2 marks, and if you have 3 correct, you get 1 mark. Part 2. Use the Born-Haber cycle to calculate the lattice enthalpy of magnesium chloride. The method for this question is that we're trying to work out this arrow, but we can't do that, so we're going to have to work around by going all the way round and using the information that we do have. So if we're going in the opposite direction to the arrow, the sign needs to flip. So for example, we're going to have minus 2 times minus 349, minus 1450, minus 736, minus 2 times 150, and then minus 76, minus 642. We've kept the minus 642 because it's going in the right direction. And if we type this into a calculator, we get minus 2,506 kilojoules per mole, which is going to be our answer for this question, which we can then write on the answer line, minus 2,506. So what I've done is I've filled in the missing information on this Born-Haber cycle. So that was the first electron affinity of chlorine and the atomization of chlorine. And because there are 2 chlorines, I've multiplied both of these numbers by 2, and then we've worked our way around to get our answer. To get the 2 marks for this question, you must have minus 2,506 written on your answer line, provided with the correct working out. Part D. Describe and explain the relative reactivity of the halogens chlorine, bromine and iodine in their redox reactions with halides, using reactions on a test tube scale. Include reaction equations and observations in your answer. Firstly, let's write the reaction equations. So our first equation can be between chlorine and bromine ions or bromide ions, and we're going to produce bromine, so Br2, and chloride ions, so 2Cl-. And what we're going to produce is a yellow solution, and this is our observation. Then we can write our second equation, and that will be between chlorine and iodide ions, so I-, and that's going to produce iodine, so I2, and chloride ions, or 2Cl-. And our observation will be an orange or brown solution. So now we need to comment on the trend of reactivity. Whenever you talk about trends, you need to talk about the direction. So we're going to talk about and focus on the trend of reactivity down the group of the halogens. As you move down the group, there's more shells of the halogens. There's also increased shielding. And with more shells and increased shielding, it's more difficult to gain an electron. So these are the 3 bullet points that we're going to talk about when talking about relative reactivity. And because it's more difficult to gain an electron, we see the reactions happening the way they do because the chlorine and the bromide ion wants to give its electron to the chlorine to make the chloride ion because it's easier for the chlorine to gain an electron. To get the 6 marks for this question, you must describe and explain concisely the trend in reactivity of the halogens. This is the 3 bullet points in this question. And describe and explain full observations of redox reactions backed up with at least 2 equations. So here we've got our observation next to our respective equation. A student investigates the reactions of two weak monobasic acids, 2-hydroxypropanoic acid, CH3CHOHCOOH, and butanoic acid, CH3CH2CH2COOH. Part A. The student wants to prepare a standard solution of 2-hydroxypropanoic acid that has a pH of 2.19. Plan how the student could prepare 250 centimeters cubed of this standard solution from solid 2-hydroxypropanoic acid. In your answer, you should provide detail of the practical procedure that would be carried out, including appropriate quantities and necessary calculations. The Ka for 2-hydroxypropanoic acid is 1.38 times 10 to the negative 4 moles per decimeter cubed at 25 degrees Celsius. So firstly, on the side, I've written a little abbreviation we're going to use just to clear up and tidy up our working out throughout. So firstly, we want to work out the concentration of A, and we're going to do this by H plus squared divided by Ka. That's the equation we're going to be using, but we're also going to be using the equation of H plus is equal to 10 to the minus pH. So what we can do is 10 to the minus 2.19, and this is going to be squared, and then divided by 1.38 times 10 to the minus 4, which is our Ka value for 2-hydroxypropanoic acid at 25 degrees Celsius. So that's going to give us our concentration of 2-hydroxypropanoic acid, which equals 0.0302 moles per decimeter cubed. And now we're going to use the equation triangle of moles divided by volume times concentration. And that's going to give us the moles of A, or the moles of 2-hydroxypropanoic acid. So we're going to do 0.0302 times 250 times 10 to the negative 3, because we're converting centimeters cubed into decimeters cubed, and that equals 0.0755 moles of A. And then we can use our other equation triangle, which is mass divided by relative formula mass times moles. And we're going to use this to work out the mass of A. So that's going to be 0.0755 times 90. 90 is the relative formula mass of 2-hydroxypropanoic acid, and it equals 6.80 grams of A. And now we need to talk about our method. So this part of the question where we're describing the method is just asking us to explain how you make a standard solution. So firstly, when making a standard solution, you dissolve your solid in less than 250 centimeters cubed of distilled water in a beaker, but we need to specify the mass of the solid we're using. So we're dissolving 6.80 grams of solid in less than 250 centimeters cubed of distilled water in a beaker. Then we're going to transfer the solution to a 250 centimeter cubed volumetric flask. And we need to ensure that the solution is all washed out of the beaker to make sure that the mass, or all of the 6.80 grams of solid, all of that is washed out and is in our solution. Then the final step to make a standard solution is that you need to make up the 250 centimeter cubed mark with distilled water. So that's making sure that the meniscus is lying on the little, it's usually a red line on the volumetric flask, so making sure that the distilled water is up to there, and then you put your lid on and you ensure thorough mixing by inverting the volumetric flask several times before finishing your standard solution and using it. To get the marks for the method part of the question, I've split it up into 3 bullet points, and each bullet point is a mark for this part of the question. So that'll get you 3 marks. Then you get a mark for working out the concentration of A, the moles of A, and the mass of A. Part B. 2-hydroxypropanoic acid is a slightly stronger acid than butanoic acid. The two acids are mixed together and an acid-base equilibrium is set up. Suggest the equilibrium equation and identify the conjugate acid-base pairs. Because 2-hydroxypropanoic acid is the stronger acid, it's going to make a conjugate base of CH3, CH, OH, COO minus. And then because butanoic acid is the base in this situation, it's going to make a conjugate acid of CH3, CH2, CH2, COOH2 plus. We can then label the acid-base pairs. So we have acid 1 and base 1, and then base 2, acid 2. To get the 2 marks for this question, you must have the correct equilibrium written, and then you need to correctly identify the acid-base pairs. Part C. To prepare a buffer solution, 75 centimeters cubed of 0.22 moles per decimeter cubed butanoic acid is reacted with 50 centimeters cubed of 0.185 moles per decimeter cubed sodium hydroxide. The Ka for butanoic acid is 1.5 times 10 to the negative 5 moles per decimeter cubed at 25 degrees Celsius. Part 1. Calculate the pH of 0.185 moles per decimeter cubed sodium hydroxide at 25 degrees Celsius. Give your answer to 2 decimal places. The equation we're going to use is POH plus pH equals 14 and POH equals minus log 10 of the OH concentration, or OH minus concentration. So what we're going to do is work out POH, which is minus log 10 of 0.185, and that equals 0.73. And then we can work out pH by doing 14 minus 0.73, and that equals 13.27, giving our answer to 2 decimal places. So if we then write 13.27 on the answer line. To get the 2 marks for this question, you get 1 mark for your working out, and then you get 1 mark for your correct answer, which is given to 2 decimal places. Part 2. Calculate the pH of the buffer solution at 25 degrees Celsius. Give your answer to 2 decimal places and show all your working. So what I've done in the top right is I've written the information from part 1 that we're going to use in this question. The first thing we're going to do is work out the moles of sodium hydroxide and butanoic acid so that we can work out the moles of the buffer. And we're going to use the equation of moles equals volume times concentration. So for sodium hydroxide, that's going to be 50 times 10 to the negative 3 times 0.185, and that equals 9.25 times 10 to the negative 3 moles. Then for butanoic acid, we're going to do the same thing but with different numbers. So we're going to have its volume of 75, then timesing by 10 to the negative 3 to convert centimeters cubed into decimeters cubed, and then multiply by 0.22. And that equals 0.0165 moles. So then if we work out the moles of the buffer, we need to minus these two values. So it's going to be 0.0165 minus 9.25 times 10 to the negative 3, and that equals 7.25 times 10 to the negative 3 moles. And we need to then work out the new concentrations for the buffer and sodium hydroxide, because we're going to be using the equation of Ka equals concentration of H plus times the concentration of A minus divided by the concentration of HA. So the concentration of HA, that's our buffer, so that's HA, and A minus is NaOH, so we need to work out their respective concentrations in the total volume of 125 centimetres cubed. So for NaOH, that's going to be 9.25 times 10 to the negative 3 divided by 125 times 10 to the negative 3. We're using the same equation triangle as we did for part 1, and that's going to equal 0.074 moles per decimeter cubed. So that's its new concentration in the buffer. And then for the buffer, we've got its moles, so we're going to do 7.25 times 10 to the negative 3 divided by 125 times 10 to the negative 3, and that equals 0.058 moles per decimeter cubed. So now we're using our second equation, and we're going to rearrange this equation. So we're going to rearrange so that we have H plus, or the concentration of H plus, as our value, and that's going to equal Ka times HA, or the concentration of HA, divided by the concentration of A minus. So plugging in our values, we're going to have the concentration of H plus is equal to 1.5 times 10 to the negative 5 multiplied by 0.058 divided by 0.074, and that equals 1.176 moles per decimeter cubed. And then finally we're going to use the equation for pH, which we used in part 1 of this question, so the previous page, and that is pH equals minus log 10 of the concentration of H plus. But in the other part we used concentration of OH minus, and it was POH. But the equation still works for pH and POH. So for pH, this is going to be minus log 10 of our concentration of H plus, which is 1.176, and that equals 4.93 to 2 decimal places, which we can then write on the answer line. To get the 4 marks for this question, you get a mark for working out the moles of sodium hydroxide, a mark for working out the moles of the buffer solution, a mark for working out the concentration of H plus, and a mark for working out pH correctly, so 4.93. Table 21.1 below gives the standard electrode potentials for 7 redox systems. You need to use this information to answer the questions below. A. Part 1. Outline an experimental setup that could be used in the laboratory to measure the standard cell potential of an electrochemical cell based on redox systems 4 and 5. In your answer, you should include details of the apparatus, solutions, and the standard conditions required to measure this standard cell potential. The general setup for measuring a cell potential is you're going to have 2 beakers with 2 electrodes in. and these electrodes are going to be connected to a voltmeter, and then connecting the two beakers, you're going to have a salt bridge. So you need to label all of this in your diagram. And then the next part of the question is identifying what's in your beakers and what your electrodes are made out of. In order to identify what our electrodes are made of and what is in our two beakers, we need to take a closer look at redox systems 4 and 5. So here's redox system 4 and here's redox system 5. In redox system 4, we're using a silver solid. So that's going to be what our electrode is made of. We're going to have silver, metal, and then in our redox system 5, we don't have a solid produced or reacting. So our electrode is going to be made of platinum metal. Then we need to identify what's going to be in each beaker. In the beaker on the left, we're going to have 1 mole per decimeter cubed of silver 1+ ions, and they're aqueous. And then in the beaker on the right, we're going to have 1 mole per decimeter cubed of iron 2+ ions, and they're aqueous. But we're also going to have 1 mole per decimeter cubed of iron 3+ ions in aqueous solution. So finally, the last bit of the question is asking us to comment on the standard conditions required. And the standard conditions are going to be 298 Kelvin and 100 kilopascals. In order to get the 4 marks for this question, you must have both cells or half cells correct. So that gets you a mark for each correct half cell. You must have a complete circuit with a voltmeter and salt bridge. That gets you your 3rd mark. And then your 4th mark comes from correctly stating the standard conditions required. Part 2. An electrochemical cell can be made based on redox systems 2 and 4. The standard cell potential is plus 0.53 volts. State and explain the effect on the cell potential of this cell if the concentration of silver ions is increased. Looking at redox systems 2 and 4, so we have 2, there's no silver ions present, but in 4 we have silver ions present. And if we increase the concentration of the silver ions, the equilibrium is going to shift right, and that's going to increase the electrode potential of redox system 4. So we can then write our 2 bullet points. Our first one is going to be that redox system 4, or the silver ion redox system, is going to become more positive. That's our first bullet point. And this is going to mean that the electrode potential of the cell is going to become less positive. So the combined redox system 2 and 4 electrode potential. To get the 2 marks for this question, you get a mark for each of the bullet points that I've written. Part B. From table 21.1, predict the oxidizing agent or agents that will not oxidize Fe2+ aqueous to Fe3+ aqueous. So what we want is for Fe2+ to be oxidized to Fe3+ initially. So that means you're going to need an electrode potential that's greater than plus 0.77. So any of these cell potentials will shift the equilibrium to the left so that Fe2+ will be oxidized to Fe3+. But the question's asking what will not oxidize. So that means that it's going to have to be anything with an electrode cell potential lower than 0.77. So the answer is going to be zinc 2+ and Ce3+, or cerium 3+. To get the mark for this question, you must write zinc 2+ and cerium 3+. Both of these you need to write in order to get the mark. Part C. An aqueous solution of iron 2 bromide is mixed with an excess of acidified solution containing manganate 7 ions. Using table 21.1, give the formula of the products of any reactions that take place. The redox systems that are involved in this question are redox system 1, redox system 3, and redox system 5. What's happening is you're starting with iron 2+, bromine minus or bromide ions, and manganate 7 ions. And so your products are going to be on the other side of the equilibrium. So they're going to be your manganate 2+, your water, bromine, and Fe3+. To get the 2 marks for this question, you must have all 4 products. A student carries out a number of experiments on transition metal compounds. 4.800 grams of a green hydrated crystalline solid A are heated in a crucible to remove the water of crystallization. 1.944 grams of water are removed to leave 0.0180 moles of solid residue B. Solid B contains 32.8% by mass of the transition metal. All of B is reacted with silver nitrate to form 7.695 grams of a white precipitate C. The green crystalline solid A is dissolved in water to produce a green solution containing a complex ion D. When aqueous sodium hydroxide is added to solution of D, a grey-green precipitate E is observed, which dissolves in excess aqueous sodium hydroxide to form a green solution. Part A. Determine the formula of A, B, D, and E. Show all your working. Firstly, using our tests for ions, we know that if we react something with silver nitrate and produce a white precipitate, we're going to have chloride ions present. So we can use this information to help us work out the formula of B. So what we need to do to start with is work out the moles of C. And C is going to be silver chloride, so AgCl. And to work out the moles of this silver chloride, we can do 7.695 divided by 108 plus 35.5. And that gives us 0.05362 moles of silver chloride. So the equation triangle we've used is the equation triangle of mass divided by moles times relative formula mass. And this is the equation triangle we're going to be using throughout this question. Next, we need to look at the molar ratio. So 0.018 moles of solid residue B has formed 0.05362 moles of chloride ions. So we can work out how much chlorine is in B by doing 0.05362 divided by 0.0180. And that gives us 3 chloride ions. So next we're going to use the equation triangle to work out the relative formula mass of B. And we're going to use mass divided by moles. So that's going to be 4.8 minus 1.944. That gives us our mass of B, which is going to be 2.856 grams. And we've worked this out using the 2 masses we're given in the question, where we're told that solid A, we heat it up and we remove the water and we're left with B. So minusing the 2 masses is going to give us the mass of B. So next, using the equation triangle, we're going to do 2.856 divided by 0.0180, because that's the moles of B, and that gives us the relative formula mass of B of 158.7 grams per mole. And we know we've got 3 chlorines, so we do 158.7 minus 3 times 35.5. That's the relative formula mass of 3 chlorines. And that's going to equal 52 0.2 grams per mole, which is the equivalent of chromium, or Cr. So the formula of B is CrCl3. Next, we're going to work out the moles of water. And by working out the moles of water, we can then find the formula for solid A. So using the equation triangle, we're going to do 1.944 divided by 16 plus 2. So that's the relative formula mass of water. And that equals 0.108 moles of water. And we can look at the molar ratio, and then we can use this to work out how many moles of water there is versus our solid B. So if we did 0.108 divided by 0.0180, that equals 6. So the formula for A is going to be CrCl3.6H2O. So that's the waters of crystallization. There's 6 of them. So now we can move on to work out the formula of D and E. So D is asking you to find the formula of the complex ion when A is dissolved in water. So this formula is going to be chromium with H2O, or 6 H2Os, and we're going to have a 3 plus charge because we've lost our 3 chlorines. Then we're going to work out the formula of E. So E is a grey-green precipitate, and we're reacting with sodium hydroxide and D. So when we react D with sodium hydroxide, we're going to form chromium OH3, or chromium hydroxide. To get the 9 marks for this question, you get a mark for working out the moles of silver chloride, a mark for working out how many chloride ions there are present, a mark for working out the relative formula mass of B, a mark for working out the formula of the transition metal, or the relative formula mass of the transition metal. You get a mark for working out the moles of water, and you get a mark for each correct formula. Part B. Transition metal complexes often have different shapes and may form a number of stereoisomers. Describe the different shapes and the different types of stereoisomerism found in transition metal chemistry. Use suitable examples and diagrams in your answer. Let's start by drawing the 3 main shapes for our complex ions. If we have copper and 6 water ligands, we're going to form an octahedral shape. So it's important we draw it 3D, and we make sure that we're connecting or bonding to the oxygen and not the hydrogen. So here I'm just completing the 3D diagram, and then we're going to have square brackets around the complex, and it's going to have a 2 plus charge. So this is octahedral. So next we're going to draw a tetrahedral arrangement with water ligands, and that's where we're going to have 4 water ligands. So again, 3D, and making sure we're bonding to the oxygen and not the hydrogen in our water. We're going to have square brackets again, but this time our charge is going to be 2 minus. And this is called tetrahedral. Finally, we're going to have a square planar arrangement, and that's where all of our bonds are going to be wedges, and it only happens for D8 transition metals. So here I'm drawing the cis arrangement of cisplatin. So we're going to have 2 ammonias on the same side and 2 chlorines on the same side, and there's no overall charge. So this is our cis arrangement, but we also have a trans arrangement where you have them on opposite sides. So we'll have a chlorine and an ammonia, making sure we're bonding to the nitrogen and the ammonia, not the hydrogen. And then we're going to have a chlorine and an ammonia. And this will be our trans arrangement, where the groups are going to be on opposite sides. So that's going to mean our chlorine and our ammonia groups. So we can have an ammonia here and here, making sure that our bond is from the nitrogen and not the hydrogen, and then our chlorines on the opposite sides. So this is our trans arrangement. So square planar has cis and trans stereoisomerism, but octahedral also has cis and trans stereoisomerism. For this question, you don't need to demonstrate both the square planar and octahedral cis-trans isomerism. But for the purposes of closure, I am going to show them. So octahedral cis and trans, if we have octahedral, let's draw its 3D generic arrangement. And then we're going to have another one. So one will be cis and one will be trans. So our cis, we're going to have on the same side our groups, and the trans will be on opposite sides. So starting with our cis, we can have OH2, or water, on the same side, and then we need a different ligand for the rest of our complex. So this could be ammonia. So this is our cis arrangement because our water ligands are on the same side. But our trans would have them on the opposite side. So we could have water here and here. And then the rest of our complex will have our ammonia as our ligands, making sure that we're bonding to the nitrogen and the oxygens. And then just to finish, put our overall charge of 2+ on both arrangements. The last isomerism we need to talk about is optical isomerism, and this occurs when you have a bidentate ligand. So if we have chromium, we can have 2 chlorines and then 2 bidentate ligands. So a bidentate ligand is when you have 2 lone pairs that can bond to your central metal ion. So if we have 2 NH2 groups, then they're both going to have lone pairs that can donate to your central metal ion and form a dative covalent bond. So we're going to have square brackets and a 2+ charge. This is our first isomer. And then the second isomer is going to be the mirror image. And that is what an optical isomer is. So here we're drawing our 3D arrangement of an octahedral complex ion. We're going to have our chlorines as the mirror image, and then our bidentate ligands, making sure that we've got the nitrogen bonding to the chromium and not the hydrogens on our bidentate ligands. So then to complete, we need our 2+ overall charge. This is a level response question, so there aren't set marking points. But in order to get the 6 marks, you must have linked together the names of the shapes and their 3D arrangements, and the 2 different types of isomerism with correct labels and examples.